All right, today we're going to tackle one of the most common headaches in electronics repair, the switched mode power supply, or SMPS. Now, if you've ever been stumped by one of these, you know that temptation to just start pulling components. But we're going to do it the right way. We're going to build a systematic, logical path to find exactly what went wrong.
You know the feeling. You plug it in and absolutely nothing. Or maybe the voltage is just completely out of whack. It's a super frustrating moment, right? But believe it or not, that dead circuit is telling you a story. Our job is just to learn how to read it. And by the end of this, you'll know exactly where to start looking.
So here's our game plan. We're going to start on the output side, because honestly, that's where the problem often is. And then we'll work our way back. We'll look at short circuits, open circuits, that super important feedback loop, and then we'll jump over to the primary side before we wrap it all up with the right way to think about any repair.
Okay, let's start our investigation on the secondary side, the output. The very first thing to look for, and usually the easiest to find, is a short circuit. The classic symptom? Your voltage just completely vanishes.
So what's the most likely culprit when that happens? Well, 9 times out of 10, maybe even more, you're looking at a shorted output capacitor or the main rectifier diode on that specific voltage rail. Now, what's really cool about this is the logic. Let's say you have a power supply with multiple outputs, like a 5-volt and a 12-volt rail. If only the 5-volt rail drops to 0, the problem is almost guaranteed to be on that line. The short is basically creating a superhighway for all the current to go straight to ground. That isolation is your first huge clue. All right, so we've got shorts covered, but let's move on to what happens when a component fails open. Now, this is where things can get a little wild. An open circuit doesn't just kill the voltage. It can make it go unstable, dangerously high, or just way too low. Man, this slide just perfectly shows the delicate dance of the feedback circuit. You've got this voltage divider, just 2 resistors, feeding a little reference IC. If that top resistor opens up, the IC thinks the voltage is way too low, so it screams at the primary side to work harder, and your output voltage skyrockets. But if the bottom resistor opens, the IC sees way too much voltage and tells the primary to chill out, causing the output to drop. See? 2 little resistors, totally opposite results. And this right here is the absolute core logic. The whole feedback system communicates using a tiny little LED inside a component called an optocoupler. If that light doesn't turn on, for any reason at all, the main controller on the primary side gets 0 information. It just assumes the worst, thinks the voltage is dropped to nothing, and it cranks the power all the way up. So what else could cause that little LED to go dark? Well, the thing that controls it, of course, the TL431 shunt regulator. You can think of this as the brains of the operation on the secondary side. If this little guy fails, the entire feedback system just falls apart.
So here's the key takeaway. A failed TL431 looks exactly like that open top resistor we just talked about. It completely breaks the chain of communication. The TL431 can't pull the optocoupler's LED to ground anymore, so the light goes out. The primary side panics, thinks the output is dead, and just unleashes its full power.
Let's actually zoom in and put this feedback mechanism under the microscope for a second. It is, without a doubt, the most critical part of the whole system, and really understanding it is the key to solving all those crazy high-voltage problems. And the star of this show is the optocoupler. So here's how it works, step by step. First, the TL431 acts like a little sensor. It's constantly reading the output voltage. Then, based on that reading, it tells the optocoupler's LED how brightly to shine. That light then crosses a physical gap, that's the isolation part, and tells the high-voltage primary side what to do. It's just a really elegant and safe way for the low-voltage side to boss around the high-voltage side. So what exactly is this PC817 thing? It's a simple but totally brilliant little device. It's basically an LED and a light-sensitive transistor, all sealed up in a tiny black box. It lets information pass from one circuit to another without any electrical connection, which is absolutely critical for safety in any power supply that's plugged into the wall. And here's the bottom line. It doesn't matter how the optocoupler fails. The internal LED could burn out, the phototransistor on the other side could break. Doesn't matter. If that light signal gets interrupted, the result is always the same, a dangerous overvoltage condition. Okay, so now that we've mastered the secondary side, let's hop across that isolation barrier and take a look at the primary high voltage side. Faults over here often lead to a completely dead power supply. Probably the most common reason for a completely dead unit is the failure of one tiny but absolutely vital capacitor. You'll hear it called the kickstart cap or the VCC capacitor. This little capacitor has one job, and one job only, to store just enough juice from the mains to give the main controller IC its first jolt of power so it can wake up. If this capacitor is dead, the IC never gets that wake-up call. The whole switching process never even begins, and the power supply is just a paperweight. No kickstart, no power. It's as simple as that.
But there's a much sneakier fault. See, after that kickstart cap gets things rolling, a whole separate circuit is supposed to take over to give the IC continuous power. That circuit uses a little diode. So what happens if that diode fails?
Now this one is really tricky. The power supply might actually seem to start up, but if you put a meter on the IC's VCC pin, you'll see the voltage jumping all over the place. What's happening is the kickstart cap gives it a jolt, gets drained, and the circuit tries to die before getting another jolt. This puts a massive amount of stress on the cap and the IC. It's basically a ticking time bomb just waiting to fail again. So we've covered the technical faults, we've looked at the components, but honestly, the most important tool you have isn't your soldering iron or your multimeter. It's your approach. Let's talk about how to think like a seasoned technician. This quote from the source material just says it all, doesn't it? If you just memorize symptoms, you're gonna get stuck. But if you understand why a circuit does what it does, well, that's a superpower. It lets you figure out problems you've never even seen before. So here it is, all boiled down. This is your mental cheat sheet. Is the supply totally dead? You're probably looking for a short on the output or a startup problem on the input. Is the voltage way too high? The feedback loop is broken somehow. Is the voltage too low? The feedback loop is basically screaming too high. Is the voltage bouncing all over? The main IC is probably starving for a steady supply of power. And please listen to this next part because it will save you so much pain. If you replace a blown primary IC, the very first thing you do when you power it on is check the output voltages. If you don't, and there's a hidden fault on the secondary side, that high voltage will instantly kill your brand new chip. Always, always check the output first. So let's leave it with this question. A broken power supply isn't just a random collection of failed parts. It's a puzzle, and it has a logical solution. The symptoms are your clues. So the question is, next time you're faced with one, are you just going to be a part swapper, or are you going to be a true diagnostician?